you. Thank you very much for the introduction. Thank you very much to the organizer for the invitation. It's very nice to be here, and it's very nice to learn about Lean and MATLib. And it's also, well, I'm very happy to be there and to be able to discuss between users of different libraries. So today is not about MATLib this morning. So it's about another library of formalized mathematics, which is in another proof assistant, which used to be named Coq, which should be renamed Rocq, so I'll try to switch name. So the proof assistant in itself is extremely similar to Lean. It's the same, it's based on dependent type theory. The basic tactics are very similar. I will speak about a set of tactics which is a bit different, a set of tactics which was developed especially to make the life of the curious mathematician easier. So this will be the topic of the talk. So you might want to, there will be slides, and there will be a tutorial. So this can be found online. I would invite you to go there on this web page and to create a code space, which will allow you to do exactly what I'm doing, to navigate through the proofs. So this will be, of course, extremely useful and necessary for the practice session after the break, but it will be already useful to have it now, just to be able to see by yourself what. This is what you want to have? So the address was also...
It's on Zulip.
The URL is on Zulip. It was posted last night by Cyril. It should be one of the very last topics in the workshop thread.
Maybe you can copy it into VS Code. Then it's
because you cannot zoom on it.
So how should I do that? Okay.
Then people can read it.
Okay, so let's go there. And this will be fun because I am not used to this keyboard. Okay. Is it okay? I'm happy, very happy to take a few minutes now if you have questions or if you need help. So, or please interrupt me during the talk if you have an issue with code space. So again, if you go on that web page, you should click here. It will build for a few minutes, and then you should have access to the tutorial.v file. Okay, and now I will talk for 1 hour, more or less, but I'm happy to be interrupted. I'm happy to take any questions during the talk if you need to, so please do not hesitate. Okay, Ssreflect. I had that here. So the Rocq proof assistant is extremely similar to Lean at the very basic. It's a bit older than Lean. It is a 40 years old as proof assistant. MathComp in itself, the library of formalized mathematics, which I'm going to speak about, is almost 20 years old. So yeah, it has different issues than Lean. It's not the same issues. It's not the same size. The community around MathComp is now smaller than the community around MATLib, but it has been maintained for a very, very long time. And I think this is what I'm going to talk about today. It's a language which was built for MathComp and which was built to make formalization, but most of all maintenance of the code easier. You are losing enough time to formalize proof. You do not want to lose too much time maintaining them for 10, 5, 20 years. And that's a real issue. The Rocq proof assistant is also known for application to the programming world. It is not a proof assistant which is only turned towards the formalization of mathematics. It has been quite successful in the certification of programming languages in the computer science world. For example, the certification of C compiler, CompCert, was quite a success. But it has been also a bit famous for the formalization of mathematical theorems. So I told you the Rocq proof assistant is old and older than Lean, but it is not the oldest proof assistant in the room. People were formalizing mathematics before we started formalizing mathematics. People started formalizing mathematics before some of us were even born. It was not the same tools, it was not the same issues, it was not the same community, it was not the very effervescent and dynamic community around MATLib here, but solutions, technical solutions to the problem around formalization has been researched for a very long time now. So I have a small list of proof assistants that you can see here. Some of them have been abandoned since then. Some of them are still in use. MISA, for example, is a proof assistant based on set theory, extremely different to what you are used to, but it went actually quite far in the formalization of mathematics. You have Automat, who is now very old, but in Automat, a book by Lando on the basic of analysis was completely formalized, and this was in 1967, so I was not here. A lot of people were not here. So it was quite a success. There's a long story of success, adding features in type theories, adding features in tactics, adding knowledge about how should you formalize this notion or this notion of math. And this is a long history, and proof assistants have been communicating with each other saying, hey, if you want to formalize topology, you should really use filters. Or hey, look, inductive types are nice when you need to formalize algebra. Or basic knowledge like that, and more advanced knowledge, which are now published in papers and in conferences and in journals. So MathComp. So you have the Rocq proof assistant, which is a proof assistant like Lean. You have several libraries of formalized mathematics in the Rocq proof assistant. MathComp is one of them, only one of them. You have other libraries of formalized mathematics, which are aiming to other objectives. The mathematical component library was at first a constructive library, a library for constructive algebra, meaning it was not assuming any axioms like the axiom of choice, the axiom of excluded middle. It was quite successful at giving a formal proof of the odd order theorem. So you have the Rocq proof assistant, the MathComp library, and you have something else, which is Ssreflect. And Ssreflect is a language. Ssreflect, at the very core, is a set of tactics. Apply, we do not have intro, we have something else. And this set of tactics is thought of as a very small and complete set of tactics, which is minimal and which allows for a very specific methodology of formalization. MathComp comes with a certain idea of how proof should be formalized at the end, how proof should be maintained in the library, what is necessary on a proof for it to be accepted in the library, for the pull request to be accepted. So, and the language, the Ssreflect language, makes that methodology possible and easier. There are other things in the MathComp libraries. There is an approach to structures, which is a bit different than the one of type classes you saw yesterday. I'm not going to speak about that. There are tools that come with the MathComp libraries, tools for example, building hierarchies of structures. This is Hierarchy Builder. I will not talk about this, so I will just show you a small part of the MathComp library, which is its language. There are other parts, but Ssreflect, I think, is enough for today. Okay, so some of you might think that the Rocq proof assistant is about constructive mathematics. This is what I thought when I was doing my PhD, and this is why I did not start formalizing stuff before. So I'm quite angry at that idea because I would have liked to start formalizing stuff earlier. MathComp at the beginning was about constructive mathematics. I am not. I am very much using MathComp analysis, and I am not at all about constructive mathematics. I have friends which are constructive mathematics, I think. I'm not even sure. It's not like MathComp analysis, which is the formalization of analysis over the big algebra analysis of MathComp, is not at all about trying to avoid axioms. Axioms and the axiom of choice and the axiom of excluded middle are put at the very beginning of the library, at the very definition of what a limit is. And so, okay, this is done. We're not about constructive mathematics. Why? So I told you the content of the slides is, I've talked about it earlier, I guess. Why customize your tactic languages, you know? Why don't you want to stick to the very basic tactics you have? So you saw that already. You saw that in Lean you have the ring tactics, that's useful. You have other tactics which give you some automation. Ssreflect is not that much about automation. Ssreflect is about maintaining the proof. It takes a lot of effort to maintain a library. And MathComp has been maintained for over 20 years now. No, not over 20 years, but almost 20 years now, by a very, very small amount of people. If you look at the number of people who actually committed into the proof of the odd order theorem, it's less than 15 people, I think. And most of them are very, very small commits. So it doesn't take a lot of people to maintain MathComp. And that's how it should be. You know, people should spend most of the time reviewing new stuff, talking to new people, creating new results in the libraries, and not building the library and making it go through time. Small-scale reflection. Small-scale reflection is something else. It's a proof technique. It's a proof technique that allows an easy transfer between mathematical-oriented definitions and computation-oriented definitions. And in particular, it allows to switch between propositions and booleans. And that's all I will say about it today. MathComp is very much using this duality between proposition and booleans. It appears a lot in the MathComp proofs, but I will not speak about it today, just know that it exists. And there are other kinds of reflections which are not between prop and bool that exist. And it's nice. Again, I will not speak about it today. Okay, so this is what I will be speaking about today. This is a logical operator. This is all the fun in MathComp, I think. For me, it's fun. I hope it will be fun for you too. I really hope it will. All of this means something in your proof. All of this makes your life easier. And all of this avoid writing unnecessary tactics and unnecessary lemma. And now we will go to see what they mean. So I will redefine everything you have learned about on how to introduce the hypotheses, how to use them, how to apply them. I hope you will follow me, but please do not hesitate to ask questions. And now we will switch to the demo. So you have this move tactic. And this move tactic allows to take an hypothesis, to put it into the context, or to take it back and to work on it. And the idea in MathComp and Ssreflect is that you will work on the hypothesis, which is at the top of the implications you have in your proposition. If you want to work on something, you won't work in it in the hypothesis. You will take it back from the hypothesis and work on it at the top of your stack. So let's see how that goes. So I have an easy lemma. Can all of you do that? All of you who would like to do that, can you do that on your computer? Please tell me if you can. Okay.
What is the question?
Can you do that on your computer? Are you able to see the VS Code part on GitHub? It's here. It's also on the README if you go there. If you go on this web page, you have a README and you can click on creating a new code space. Okay, so let's see. So I want to prove that if n is divided by 2 and m is divided by 3, then 6, otherwise known as 2 times 3, divides n times m. Okay, should be possible to prove that. I think we can do that. The first thing I want is I want to be able to handle m and m. And I'm going to do, please take these two natural numbers and move them to the hypothesis. And this is what this move will do, okay? And now I think that I have an implication, and I have a top hypothesis here, and this is always what I will be working on while doing my proof. So maybe I want to put the hypothesis in the context, but maybe I don't want to. Maybe I'm saying, yeah, I think I would like to break this hypothesis. I would like to work with the two parts of the hypothesis separately. So let's put it back on the top of the stack. And this is what my move 2 points is about. Yeah, I just want to take that. I am never going to work on something which is here. This is something you can do, of course. There are tactics which allows you to do that. You don't want to. You want to be very, very strict about where you are going to work on your things. It's much more easier, believe me. And now I'm going to say, okay, I don't want to introduce H. I want to break it in 2 parts. There are several ways to do that, but the easiest way is to use this notation, saying, hey, there are 2 elements in my hypothesis, A and B. Can you break this hypothesis and just name directly A and B? And it's easier, I think. It works. There are another way, another structure of hypothesis I could have. So we just looked at conjunction. You also have disjunction. And you can do the same. It's not exactly the same notation because it won't have the same effect on your proof. So again, I took a lot of stuff from the top of the stack. I could have done it like that, you know? I can introduce an arbitrary number of hypotheses, of course. But now I'm like, no, I don't want to. Maybe I want to work on H again. So I could have done that directly, you know? I have introduced M and M, and now I want to break my my hypothesis in 2, but since it's a disjunction, it won't look the same. Once I've done that, I will have to prove my proof twice, once under each part of the hypothesis. Meaning here, I want to prove something which is not true, maybe. But I think we can survive with a false proof being admitted in this tutorial. Maybe I will put something else here. Yeah, I will put a board. But so now I want to prove that if I have this left part of my hypothesis, then my conclusion is true. And if I have my right part, then it is true also. So this is exactly what this tactic will do. And I think in Lean, I don't know what it would be. It would be distract or something like that. It's very similar. Okay, great. In the Rocq proof assistant, in fact, it would be different without the Ssreflect tactics.
Can you explain the difference between admit and abort?
Admit suppose that it is true. Abort is saying, yeah, let's not continue towards that proof. It doesn't.
Yeah, but in practice, it means that you cannot use the lemma later?
Yeah. Otherwise, I would have been able to use debor, which I don't want to. What else can we do? So this was very much like, what else can we do? Sometimes you might not want to introduce your hypothesis. Sometimes you want to say, hey, just leave that at the top of my stack. And this is my plus here. Yeah, maybe I want Y to stay around here. So I will not name it, I will put a plus and it will stay here. Okay.
Do you have an example of that?
Yeah, I have an example of that. I have an example of that, but I wanted to show that before because that's almost more important. There's a lot of trivial stuff that you don't want to prove. And trivial stuff is proved by these signs. You have a sign that tells you just eliminate all goals that are exactly like the hypothesis I already have. If I know that my set is empty and I want to prove that my set is empty, then just look in my hypothesis and don't ask me to explicitly tell you which hypothesis I'm going to use. You have something else which tells you just compute. If I want to prove that 6 is equals 2 times 3, maybe try and compute that. Maybe I don't need a lemma to tell you explicitly that. Maybe this is just mere computations. And this is why you will see a lot of these signs appearing in proofs. This is what you should do by default. Hey, let's see if we can simplify by computation and by everything which is a bit automatic in our proof assistant. Let's just do that all the time. And you have something else which is do that by blah blah, and the by will encapsulate everything that is easy. So let's go and see some example. Okay, I am using an intermediate lemma here. We will see more of that notations. And now I want to say that maybe 6 here is equal 2 times 3. So how am I going to prove that statement? So let's see what was happening. I had one statement, but now I would like to use something else. I would like to replace that here by 6. There's a lot of ways of doing that. The most basic one being explicitly introducing this goal, which is going to create that. And this is how I will prove it. Okay? This wouldn't work. It won't change anything. This would work. I have other ways of proving that. I can forget about my hypothesis. What is not working here?
Because you changed the slash in
Thank you.
Can I ask something? What do you mean? What is compute? Like what does it kind of allow to compute?
Like compute on an inductive type, for example, on inductive definitions. You can compute on natural numbers, you can compute on booleans, you can compute on stuff like that.
It's like decide in the
what?
It's like decide.
Okay.
It looks like I wouldn't. It looks like it.
Like kernel reduction. Okay.
But in practice, then there are actually
Finite
different
computations.
Yeah, in practice, finite computations. I'm not sure it does everything you want to do in the kernel, but
It's a simplification heuristic. Okay.
okay.
Reducibility is simp, or is it simpler than simp?
It's less than simp, I would say, in lean. It's much less than simp.
So after more basic, after you introduce 2 times 3 equals 6.
Yeah.
Now you don't have to prove this right away. You can use it right away.
Yeah.
Okay.
I can also. It's very hard for me not to show you all the things I could do to make that proof easier now. But there's a lot of things we could do.
Okay. No, but the lean syntax is that after a help, you have to prove the help.
Yeah. This is.
Here you're using it, and then you are.
Here I am proving it.
Yeah, this is the proof. The move slash equals is the proof.
This is the proof. It's not just well indented, but this is the proof.
This is the proof of 2 times 3 equals
Yeah.
6.
Yeah. And I have a simpler way. So I am forgetting I am discharging that. I am forgetting that I proved it. This is my syntax for doing that. And yeah, forget I have H. It's exactly the same thing as just deleting that whole part of my proof. And that's another way of proving it by I have nothing to do. It's just immediate. And then I can use it using the rewrite tactic, which looks a lot like Lean. There is something else I could do, and I think I want to show it now because otherwise it's too painful. Let's prove another version of that. So we already saw that I had a simpler way of doing that. Maybe I don't want to rename. Where is it? It's here. No, it's here. Yes. Okay. I even don't need to name my hypothesis. I can already describe how I want to use it. And this little arrow here is saying, once you have proved it, just rewrite it. So I'm doing 2 steps in one. Which is, that's a good example of what Ssreflect is about, is not naming the things you don't need absolutely to name. So,
Why do you have an admitted at the end? Let's prove it now. No?
so that's my proof.
You don't need
Yeah,
71,
I mean,
you don't need
line 71, right? I mean, after this,
That's the proof of the lemma, of the equality between 2 times 26. But you still need to say
No, no,
that
it's
you
done. It's done. Line 71 can be removed, is the question.
971.
71.
line
It's not
66.
you still need to notice that it's in the context, right?
No, I can't. I haven't finished my proof here, but I can finish it, of course. I haven't told explicitly to the proof assistant, just do that, please. Okay, which is just go and look in the hypothesis. But I think this would by have work. This wouldn't work. Also, there's a lot of other things which. So this is not, of course, the shortest proof you have of those results. There are shorter proofs. This is not what you would like to write in the library, but it shows you all the things you can do. Other things you can do, sometimes because your lemma is not well written, or you are part of a much bigger proof, you want to discharge hypothesis, and this is a curly bracket notation. It's extremely useful because when you have a really long proof, you do not want to stay with 21 hypotheses in your local context. You want to have just the hypotheses which are necessary for now, but you want your proof to stay readable, and you want your proof to take not too much space in VS Code, otherwise you won't survive. A simpler way of doing that is saying, yeah, I don't need my second hypothesis. I won't name it. Just forget about it. So let's go over that slowly. Here I introduced a number m, which I don't need. So this will just change my context. Another way of doing that is saying, yeah, I know I need several natural numbers here, but in fact, the second one is not needed, so just forget about it directly.
But there's a small difference. At the end of line 75,
yes,
you end up with blah 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 equals true. Whereas on the end of line 80, you end up with just blah blah blah.
Good question. I wouldn't know how to answer.
What is the exact?
Why do I have true here?
There you have that blah 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 is equal to true. Whereas on line 80, you just have to do the 2 times 3 divides n.
I have the answer, but it's very complicated.
I don't want to know.
It,
well,
it doesn't stay in the margin.
So maybe what I can say is that it's underneath, it's the same term, but there is one particular use of move that unfolds what he did by accident here. So this is really accidental, and I never saw that before.
Neither did I, because usually it's not what you're trying to prove.
Yeah.
But yeah.
Usually,
no, I agree that line 75 is constructed for the example.
Thank you. So I think we just saw a lot of things about proof management, how to manage your hypotheses, how to name them, how to break them, or to make them usable. The next thing you want to do, I think, is rewriting. Even before applying lemmas and applying hypotheses, I think you already know that a lot of time is going to be spent on just rewriting lemmas. And you want that to be as efficient, as short, as easy to do as possible. And that's another feature which is quite important in the Ssreflect tactic language. You want to be able to chain rewriting lemmas as easy as you can do so. Now you have tactics like ring and things like that in MathComp, but it's quite recent. It was working in the Rocq proof assistant, but it was not working with the whole hierarchy of structures which is in MathComp. So you really needed your rewrite to be easy to do, otherwise it was hell on earth. So what can I do? I can do a lot of things. I can rewrite on one side, rewrite on the other side. I can rewrite always, which is the exclamation point. I can rewrite maybe if I need to, only if I need to. and that's the why not here. I can rewrite in a pattern, meaning I can say, hey, can you write exactly in the expression that look like that, in a very subpart, in a very small part of my goal. I can compute, I can use rewrite to do computations. So this is A transformed into B here. And I can use rewrite to unfold definitions. And meaning all of that can be done in a sequence, in one line. I can unfold the definitions. I can look for a certain pattern and rewrite in it. I can rewrite maybe in all the implications I will have. I can do all of that in one line, and that makes your proof short, and that's a way of not naming explicitly the hypothesis you're going to have.
I have a question.
Yes?
Does copyright work under binders?
Not by default, no. We can look at examples later if you want. So I think that's a lot like Lean. Is it exactly the same? Cyril is saying that not exactly, but I think, yes.
You have that to say rewrite and apply by
yes,
brackets?
by rewrite. So, yes, so let's look at what we are doing now, but this is too much detail, and you can do by arrow. Please do by arrow. So I can introduce H, and now I want to say, okay, this is trivial as long as I know what I already know, that M is equal M, but this is something which I still need to tell my proof assistant, you know? So please use that lemma and rewrite, and now it's trivial. A lot of things would work here. I could do that. Okay, this is exactly what the / is doing. It's looking the context. I could even not just put the / here in the sequence of rewrites because I don't want to write explicitly move. I'm not explicitly taking something and putting it in the context. I'm just simplifying. I could, in fact, not put a point here, but just put something like that, which does it all in one step. The point breaks your computations. This notation here just allows to chain different tactics and different commands. I think you have that also in. Okay.
Can you say again the difference between the period and the semicolon?
The semicolon is going to allow you to chain your tactics, not to make the intermediate result between each tactic visible in your proof assistant. So there is a difference between doing that. Here I can see what the intermediate goal is. If I do that, it's just one step. Yes?
So the point is the equivalent of Lean semicolon, and the semicolon is the equivalent of Lean bracket semicolon.
Ah. Uh-huh.
I can also do that. I can also, everything that's easy, I can replace by a by. That's also one other way to do it. Of course, I may want to rewrite to change n by m. I may want to change m by n, and that's possible. And sometimes you want to do that. Yeah, so this is what I was telling you about. The semicolon is just to change several columns on one line. There is something.
If you want to write two hypotheses one after the other, can you put a list of
Yeah. Yeah.
brackets,
Yeah.
blah, blah, blah,
Yeah, yeah, yeah. So there is something I really want to show you, but when I was writing this demo, I was telling myself I should be slow, so I will try to do it one example at a time. So we have that. Here we don't need any computation, in fact. This would work also. This is what I was telling you about. There are several ways of putting simplification, and simplifications can always be written in a chain of rewrites. You don't have to put the arrow here. The arrow here is the same thing as telling move arrow. Move can be deleted most of the time. Move arrow can be deleted most of the time when it's not at the beginning of something else. Move is just something which is very transparent. Move is here to allow you to put an arrow or another sign after that. But move is really something which is quite transparent. It's the same thing as doing that. What else can I do? Yes, and this is what I was telling you about. The preferred way, and when you look into the MathComp library, you will see that most proofs end by by, because there's a lot of things in by that are not, there are hints or things like that, which are not directly in that kind of sign. So you might want to just end every step of your proof by something which tells by. This is how I will conclude my proof. Okay, and it was very painful for me to show the previous examples because you never want to explicitly name an hypothesis that you're going to use just after that. I mean, who would do that? Like, I mean, don't lose time doing that. Just, instead of naming it, just tell the proof assistant how you are going to use it. That's the only reason for the hypothesis to be introduced. You shouldn't have to name it. So here, what am I telling my proof assistant? I am just telling, yes, I know, it's not finished yet. Let me just make my proof assistant happy. And I'm not sure I know how to, yes, right here, okay. Instead of naming explicitly this hypothesis, I am just telling you that you want to rewrite with it. And you might want to rewrite in one way or in another way. And that's what the arrow is doing. You never want to explicitly name something that you are going to use just here, just after. And everything in Ssreflect is done so that you don't have to name things that you don't need to name. You have a way of avoiding to name explicitly intermediate lemmas. You have a way of immediately breaking your hypothesis without even naming them. You have a way of directly rewriting with hypotheses while you are introducing them. You have a lot of things that we are going to look at now. You have a way of directly applying a lemma to your hypothesis before even adding it into your context. You have a way to feed an argument to instantiate your hypothesis before even putting it into your context. Yes?
On line 117, do you need the first arrow?
Yeah. No?
If you just do move and then the normal arrow.
No.
Move, it's a shortcut.
It also works, no?
It's just.
Which arrow are you talking about?
Just the first one, the one with the equal. If you take this away.
Whoa.
It's a shortcut.
No, I had no idea.
Usually you don't use it because this is a toy example, so there is only one rewrite, but usually it's a chain of things.
Yeah, usually you would have an apply after that.
It works, but forget about it.
But you will never use it in practice.
The first good idea, but then forget it.
Yes.
And so can you also substitute equalities within such a move sequence? Yeah, I mean you can use rewrite, but
Yeah. I'm not sure what the question is.
You can rewrite also in the context.
Everywhere.
You don't want to rewrite in the context. I'm being a bit strict here, but you could, but I'm not sure this goes with the methodology we are using here.
Because with our intros, you can, if you call your hypothesis RAFL, then it doesn't, like it destroys it.
So there is a tactic to do this, but it's deemed unstable because one principle of stability of this language is that you should not touch an hypothesis which name doesn't appear explicitly in your proof.
This is why I was like, yeah, you should not do that.
If you do it, means you can have unpredictable behavior later on. If you extend your context with more stuff, and then suddenly substitute things in places where the initial proof wouldn't have.
Okay.
So maybe I'm misunderstanding something, but I personally rewrite in the context all the time.
Yeah, but
the name
you should not.
With regard to changing everything around. I mean, the dogma here is that
Okay.
local.
That I see. Okay.
So let's.
Can you do this and still keep it at the top of the stack?
Yeah, I think I could. This is a dupe. So we are going into very.
Keep it at the top of the stack because you might need it.
okay.
Dupe.
The slash bracket.
So we are going into very advanced question by advanced users of Lean. I think I would also like dupe. I think I would.
And then give a name after dupe.
Yeah. Okay.
No, I don't want in context. I want to keep it at the top of the stack of the row.
Plus.
Okay. Yeah.
But we are going into advanced question of advanced users, and I would still like most people of the room to have an idea of what we can do.
It's just not advanced. It's you are dropping some hypothesis, and it makes us nervous.
My way of doing that is that if I know I'm going to do that a lot, then I would name it. I would keep it in my context, and maybe when my proof is done, I can see if I can simplify stuff, but I would never rewrite immediately with something that I have a doubt that I might use it later. I might come back on the proof and make it shorter, but in the first attempt, I wouldn't do that. You can change rewrite, you can change arrow, okay? You can do that. So I have n that equals m, I have q that equals p. I want to rewrite with all these equalities. I can do that one step at a time. But I can also do that in one step, okay? So that's possible, and of course it can be arrows on the left or arrows on the right, works the same. And I'm just doing that, or I can do, I don't know, this, which is the exact same thing as the by I had before. Okay, so let's go into patterns, which is what I was telling you about. So I've told you, you don't want to name explicitly your hypothesis when you don't need to. In fact, you don't want to name explicitly your arguments when you don't need to. When you need to rewrite, to use, for example, here we are going to use the commutativity of the addition. But you don't want to tell you, I will use the lemma saying that addition is commutative for 1 and 2. You want to say, I want to use that lemma on this subpart of the term where there is a and a b or a 1 or a 2 appearing, but I don't want to name them explicitly because their name might change because several reasons. So let's see how it goes. Let's see that I want to prove that. Is that true? Is that true? Yes, it looks like it is. Okay.
Is a ring type commutative?
No.
No. Otherwise it's not true.
Yeah, so it's not true. It should be a commutative ring.
No, but multiplication.
Yeah, but multiplication is not so it's not true.
From the right to the left.
What?
Yeah, Q here, it's not going to be true because I don't know that multiplication is commutative.
Ah, yes.
Okay, let's still try.
It's not about true statement.
It's not about true statement. So I could do that. There are several additions I might want to rewrite. And let's say I want to rewrite the one which uses Q. I might want to explicitly tell that I want to use Q. I also might want to tell I want to rewrite using the pattern that looks like that. I might want to say that I want to rewrite inside the sub-pattern the subterm which is being multiplied by q. I might want to say to not even name q, but to name just the thing that I want to rewrite in and to leave the context empty. I might want to say that I want to rewrite only in the right-hand side of my equality. So sometimes you want to rewrite at some very specific point of your goal, and you have several ways and a lot of ways of doing that. And the preferred way is really using this kind of context. You want to use the structure of your goal and not the explicit name of your hypothesis.
What is IDR?
So let's check what's added.
And the percent E?
So yes, this is something you might not want to see, and we could try and make you not see it. E is saying extended because I am using MathComp analysis here, and so most of the time I'm going to compute not in NAT, but I'm going to compute in the extended reals. Okay. And this is because I imported a lot of stuff at the beginning, so this is, hey, this might be at the infinity, just be aware of that. Yeah.
I'm fixing it right now.
So Cyril is fixing it right now. There are two goals to the tutorial, you know, showing MathComp developers.
Can you go over line 147 again? Because I don't understand exactly. So this says, well, rewrite.
So before I said I had a pattern, and I wanted to rewrite in what was in here, okay?
Right.
And
so you are rewriting in the underscore.
Before I was, now I'm rewriting here.
So on line 146, you're rewriting on the q plus p, which is on the
yeah,
line, on
yeah.
Part, okay?
So we can see the difference, I think. This is what is changing.
Do it again. Okay, great. And below you are rewriting. Oh, both.
In the X here, because I don't want to name explicitly what's in my context. This is what I did before, you know, I was naming explicitly the context. Now I don't want to name it, and instead I'm going to put one X, and the X is where my lemma is going to look for.
So does it mean you're rewriting inside the subterm selected by the X?
Yeah.
Or does it mean that X itself has to be rewritten as a whole and match the rewriting rule?
X itself has to match the rewriting rule.
Sorry?
I think I would say the same.
It has to be of the form A plus B.
Yeah.
Can it be a complicated sub-expression inside which you will do this rewrite every time it matches?
I think we could. Yes, I think we could.
In X.
If X is not exactly a plus, then you would. No?
The other side.
Yeah, sorry.
That's nice.
But yeah, it's beginning to be long, but yeah.
Can you explain again the difference? Sorry.
So here, when I'm writing that, I'm saying X should be A plus B for some A and some B, because I'm going to rewrite that. If X is not exactly A plus B, but X is something in which I can find X plus B, then I need to tell explicitly that I'm looking for a sub-expression in X, and that's in X. But my way of doing that would be describing the pattern more explicitly, because in the first approximation, it would be easier for me. But maybe after that, I want to come back on the proof and identify a simpler way of describing my pattern. There's always a difference between what you would do in your proof, in the first version of your proof, you know, in what you are writing for you or for your colleague, and what you are submitting in a pull request, what you are submitting to the editor. There's always a difference, and there are things here that the experienced user will write first. There are some things that even the experienced user might not simplify first. So that's a difference. I really want to go to the apply, because rewriting is important, but applied is even more. I'll just show how you can do unfold definitions. Unfold definition is also done through the rewrite tactic, and it's just the term you want to rewrite or the notation you want to rewrite. So here, I'm looking at a goal which is a bit new for me, and I don't know what is this weird symbol. And I will just do something very ugly that you should not do, but we will do it, but don't be afraid. Okay, so here it goes. This is telling me, what is it telling me? Yeah, this look like scalar multiplications. And here you are seeing things that you should not be able to see. It is just the explicit construction of the structure. It should be simplified. Maybe I don't want to do that, and I will just rewrite it, refold it, and refold it again, thanks to the exclamation point here.
When you, the first time it unfolds it completely, but then the second time it just folds it a little bit.
I don't know why.
No, okay.
But yeah, but this is something that I will never leave in a proof. But sometimes I just want to know how scale is a keyword here, and I'm looking for lemmas using the scale keyword if I want to speak about scalar multiplication. Because sometimes notation should work, but sometimes maybe I will have too much lemmas and I want to also say the name of the lemma. So we are going to go into more details over how search works. This was just an example. So we don't have, I want to say Moodle. We don't have Moodle, yeah? I was saying Moodle, but that's teaching stuff for French people.
GPT-4 does a pretty good job at...
We have GPT-4, but you have to pay for it. So we have search, and search works well enough, very well, in fact, for me. If search doesn't work well, you have Zolip, but otherwise...
But this doesn't do anything. After you do a search, you just get an information.
Yeah, it's just it's like check, and it's just search. And there's a lot of things in search. You can search by pattern, you can search by name, you can search by a lot of patterns, you can do a lot of search. And this is very important when you are beginning to formalize, because when you are formalizing stuff which are a bit intricate, you are going to spend all your time looking for lemmas, half of your time. You have to know it, and I don't know if you have to accept it, but that's the current state of things. Anyway, I will just... you have the search pattern, you have the check pattern, and I just wanted to show you that now, thanks to rewrites, of course, we are able to prove the first lemma, which is correct. The second was not, the first is. Okay.
What's the difference between check and search?
Check just gives you the type of your lemma.
Okay.
Print is going to be something else. Print is going to be to show you the...
There was no question about...
Oh, but, sorry.
Yeah, but you gave the
But let's... I can search ghosts. Let's look for all the lemmas that contains... I'm sorry, I'm on an AZERTY keyboard and I'm suffering here. Okay, let's search for all the lemmas which have ghosts in their titles in the libraries we imported. And I did not import all the libraries available because I don't need them. Okay, yeah, there are some things which you should not be able to see, but let's stay here. My way of doing that is that sometimes I want to have all the lemmas possible. Sometimes I just want to have a subset of them, so I will refine. I will give a pattern, or if I know exactly what I'm looking for, I'm going to be very specific in my search. Otherwise, I prefer to have time to scroll down the list. So this is what I just told you. You can search by name, you can search by pattern, and you can search in specific lemmas. Maybe I want to search in the topology library, and I don't want to search in the arithmetic library. I don't think that I don't think this is going to give me anything, in fact.
Can you search for a lemma which applies to the current role structurally? Or
Sorry?
can you search whatever lemma will apply to the current role?
No, I don't think I can. But it would be nice. But no, I can only, it's a very external search to my current goal. Okay, so we officially told you that we were going to stop at 10:15, so I think I will take 15 minutes and we will stop for a good half an hour after that. I told you about moving your hypothesis and your arguments. I told you about rewrites, and there is something else I really, really want to tell you about. It's application. Application is made extremely easy in the Ssreflect language, and it's what is really fun in my point of view. Yeah, I do like that. Thank you, you're nice. I had a. I can apply a lemma, as always. You know, I know that A implies B, and I want to prove B, so I will say apply H, and then I will just have to prove A, and hopefully A will be easier to prove. I might let's look at the third line. I might want to do that on my hypothesis before introducing it. And that's going the \lemma, which is going to happen here. I might going not to apply a lemma on H, but to feed something to H. And that is what am I doing here. That's the syntax saying, hey, I have my hypothesis, just give A to my hypothesis, and then introducing it once you have fed A to it. So I think this is much more clear on example now. What can I do? Okay, I can do apply. Sorry? Yeah. But with moves, and just know that every time I'm putting move, I'm just writing move because I have nothing before. It could be a semicolon. But since this is the first thing I'm writing, I need to explicitly write move, otherwise I wouldn't have to. What can I do? I want to prove this very difficult lemma. I can just introduce the proof of H and the proof of P, and I want to prove P. I will apply H, and it will be then by simplification. No one wants to do that. This is one other thing you could do. You could just introduce H, and then instead of introducing P, just directly apply H to P, and not name it. And then you would have something that's easier to prove. Of course, it also works when you don't write the explicit and intermediate move, and you just put the by at the beginning of your sentence. Sorry, just going there. Okay, that's.
So if you don't want to name it but apply it directly, there's a syntax for that.
Yeah, there's also a syntax for that, and I think it's just what we have after. Views, so this is called a view. Doing that, view can also be used with equivalencies. There's a lot of lemma saying these two structures are the same, these two structures are equivalent. You don't want to split them to be able to use them. You just want to apply them on the go, and this is possible. It's like rewriting with equivalencies, and that's called a view. That's called an applied, which is done better.
Sorry, I still don't understand this slash H.
So let's break it. H is the fact that P implies Q. Now, instead of introducing P, which would be done, I might want to apply directly H to the hypothesis which is on the top of my stack, which is P here. So I'm going to, and again, I'm going to do a move which should be transparent here. So let's look, what is it before, what is it after? I just applied H to P. We are going to do that with examples in small shadings. This is pure.
Maybe you can do an example where what you need to prove is not literally H.
Yeah, maybe I will do that, but I just wanted to show it on simple examples.
So, okay, so this is not backward reasoning. It's, you have P.
It's avoiding to name things.
Okay.
It's not.
It's intro apply. So it's doing intro apply H. If we say no, it's strange.
Yeah, we will see a lot of that.
It's intro, then have H applied to HP, then revert that.
Yes.
And clear the name.
And clear the
no,
name,
no,
because
not in
not in
this case.
the case. Okay.
Yes, import and specialize, and then you do that.
Say it again?
No, because then you would lose H. You still have H in the context afterwards.
Well, here, no.
Let's look at the other features. I don't know why, but I just love that. It's even better than views. It's like just instantiate as soon as you can if you know you won't need the whole generality of your lemma. And it has been super useful for me. I don't know if it's specific to what I've been formalizing, but so here I have P first, and then I have P implies Q. I have to introduce HP, but I might not have to introduce P implies Q explicitly. So what am I doing here? I had that, but I'm feeding P to it explicitly, and it's just giving me what I want. Super useful. We also have a way of keeping the hypothesis in the on the top and just introducing what you want just after that. This is what the plus is doing. It's an advanced feature. It's not super useful. Okay, and this was view. I think so. All these things on rewrites and view, you can do them when you are doing intermediate lemmas, when you are doing backward reasoning, okay? You can do that on your hypothesis, but you can do that on the intermediate lemmas you are proving. And this is, I think, where it is the most useful. You might want to prove something and know that you are just going to rewrite with it and just tell that to the proof assistant and not try it directly. You might want to apply a view directly to what you are proving and introducing like that. And there I am proving something, I am applying a view to it, and then I am breaking what I have in two and introducing only A and B in my context. This is a bit advanced, but just to show you that, of course, these are not the key example where you need this kind of tactics. You need that when you have a lot of intermediate lemmas and you want to keep your proof short and usable and readable. You also have the case tactic, which is going to destruct. So I don't know what's the equivalent in Lean. It's going to be R cases. But can you use R cases to take something from the context and put it back on the stack? So it's going to be R cases also. So that's...
Nothing reverts.
Okay.
Except for reverse.
Okay, so we do that a lot. And you can use case with the arrow as move. You can also use case to take something from the context and work with it, because we are always working on the hypotheses which are at the top of the stack. We don't have to, but that's a kind of methodology which is present in MathComp.
Sorry, when you say at the top of the stack, you mean?
Top of the high. So you have the context. Let's go in on the...
Just to see what you mean by top of the stack.
That's the context?
At the top of the context.
No, and that for me is the top of my...
The goal is the same.
Interesting. The goal is
And the top of the stack is the left part.
It's the first argument of the function. You think of it as a function.
It's the left part.
Because we will never work with that. I mean, if you see an implication, if I see an implication, I start immediately with intro, just the implication.
Yeah,
No,
this is not what we are doing here, and it's interesting. It has the advantage of being very strict, so it's easier to maintain, and if everyone does that, then it's a kind of a collective methodology which works. So that we already saw. Instead of doing that, I think I could do case. I hope it would work. I never use case like that, so yes, you can tell explicitly that you are going to break your hypothesis, or you can use a bracket, and I do prefer to use a bracket whenever I used to. You can also use case to compute on things that can be computed. Here I have a Boolean, and I know my Boolean is either going to be true or false, so I'm going to use case to say, just compute, just break my Boolean, and then you can compute with it. I can use case on...
So what is the statement of 250? Is it B1?
B1 or not B1? To B1 or...
Or not?
So I don't need B2 here. I just need... So this is to be or not to be. Thank you. I'm sorry. So let's see what's happening when we are only doing case B, okay? Case B is breaking B, as it is an inductive definition. And of course, then it's going to be easy. But it's not only Booleans. You know, there's a lot of things you can compute with, and you can also compute with natural numbers. Okay? The case here, this is trivial. I'm saying a natural number is either going to be 0, it's going to be bigger than 0, and this is by definition of the natural numbers. And I can do case on that, and a lot of automation is going to take place on natural numbers. In the last minute, let's see something which might be a bit more complicated. So in fact, I was looking for this proof in the MathComp library, and we noticed that it was not in the MathComp library because no one needs that to prove something that is proved in the MathComp library, so it's not in the MathComp library. But it's quite easy to prove. What might we want to do? So you might not be able to, you can read that in a good way. You might not be able to read that because it uses some logical stuff on it. The first thing we want to do is we want to apply something which is a view, which is something that allows us to navigate between two descriptions of negation. And you don't want to see that. But it's a view. We are going to do some stuff that makes our goal easier. Now, we want to prove that there is no such x such that x is rational and square root equals x. And then we want to break that. We want to suppose that we have x, and we want to prove that this is not true. We want to prove the false. So we are going to use case here. And then we are going to use some nice characterization of rational numbers, and we are going to put that back in the context and work on it. So this is, sorry. We have that. This is telling us we have a nice description of rational numbers. I am going to put that back in the context thanks to a move. And then I am going to break it. And this is what I want to use. This is nice characterization. Rat Bezier is already assuming that 1 is even, like P is that not to the two numbers are even. So this is what I want to use in practice. I'm going to destruct that, and I'm going to move forward with a proof. I'm going to use rewrites. I'm going to use a view here, which is a bit complicated. I'm going to use something else here that I haven't told you about, which tells you that it's enough to prove this intermediate lemma, because sometimes it's easier to prove a bit more. So I can do that. And that's it. And that's, I guess, it's the end of my talk. I just wanted to, there are other things that can be added. You have the MathComp analysis, which uses other tactics that allow for, to avoid the explicit handling of epsilon notations and to allow to just state that I am near my goal and that's enough for me, and I don't want to state explicitly now or never how close I am to the point which is in my neighborhoods. There's a lot of materials available on MathComp and Ssreflect. I would advise, if you're interested, I would advise to go on this one of these two links, but do not hesitate to ask questions in the break if you need to. We will go through a practice session. The practice session is just here to help you move things around, break stuff, use views on quite simple lemmas. We have, I think, a bit of number theory and a bit of topology so that everyone is happy, and we will be here to help you if needed. Thank you for your attention. Oh, sorry. Yeah, happy to take any questions.
So, in the first example, first exercise you proposed,
it's the at the bottom, at the back.
No, because it's recorded. So Flo, no, it's recorded. Please.
Yeah, in the first example you proposed, so can you extract something from A using case, like some n prime such that 2 times n prime is equal to n, or?
Yeah, I think this, I would have to go through a view to do that. Some explicit lemma which tells me that I have an equivalent description of A, and I'm not sure. So let's try and do it, but I'm not sure. I think it won't lead to, yeah. It doesn't lead to anything. Sorry?
The equation, there exists K?
Yeah, that would be div P.
Div and P, or div and search div and P2.
Something like that?
I don't remember. Maybe search div and Q as it means.
I'm struggling with my keyboard. Yeah, sorry. So the answer is case would not leave you directly. You would have to do as we did for rational numbers, using some explicit lemma which gives you the good characterization, and then use that to break your hypothesis.
while A is in the context, or
Div and P,
you have to
so
put it
it's
back
div
in
and
the goal?
Sorry?
Do you have to put A back in the goal to do that, or is it at first?
I will do that, but while doing my view. The preferred way to do that would be to have the view here.
Slash DVD and P.
DVD and P. That?
DV without the I, no I.
Okay. Yes, okay, that's it. This gives us, and then I can do case A, or I would prefer to break directly A here.
So, any other questions? Yep.
Well, first of all, I wanted really to thank you very much for the beautiful talk. It was extremely inspiring. I wanted to wrap up. So you said it at the beginning, Ssreflect is a collection of tactics that is specific to MathComp. So what you've shown us today is those are all tactics that are part of Ssreflect, but not part of Rocq in general. I mean, so what's the link between what you've shown and what is exactly Ssreflect?
Ssreflect is a set of tactics that you could import while doing a proof in Rocq and not using all the MathComp lemmas. Now that Ssreflect is already almost between 10 and 20 years old, so it has led to things that are now integrated in the core Rocq tactics. There are good ideas in Ssreflect, and they were imported in Rocq tactics. Most people that do not use MathComp won't be as strict on everything I told you. Do not go and rewrite in the hypothesis. Views are something that I have not seen a lot outside of MathComp, but it's always possible to import Ssreflect, and I think there are some tactics that looks like Ssreflect, but are named as with another name. So the Rocq tactics are very inclusive. There are a lot of Rocq tactics. Rocq has been here for 40 years, so just imagine the number of tactics you have, and it's a choice from MathComp to be very restrictive on the number of tactics you are accepting, and to have tactics which are very modular, so that to not introduce too much new tactics, and so that for it to be easier to maintain, so for not to introduce too much stuff.
Thanks.
Yeah, thanks a lot. So I suggest that we go to the coffee break now. So let's thank Marie again.
Thank you.